Okay, so in each of the questions above, we want to find a vector that is perpendicular to the surface at the given points. Okay, so remember, let me just remind you, when you have a surface of the form f of x, y, z, we have a surface of the form f of x, y, and you have some point x naught, y naught, z naught that lies on the surface, then a vector that is perpendicular to the surface at the given points, you can just take to be the x derivative evaluated at x naught, y naught, the y derivative evaluated at x naught, y naught, and then minus 1. Okay, this is a vector that works. And why is that? Well, let's go up to this example. Okay, I'm going to write in red on this example. So really, a vector that is perpendicular could just be the normal vector for this surface. Okay, so the normal vector to this surface is perpendicular. So this is a plane. The normal vector to this plane is perpendicular to the plane. But also, since this is the tangent plane, it means that the normal vector is perpendicular to the surface at the point 1, 1 e squared in this case. Because that's the point that we're looking at, 1, 1 e squared. Okay, well, if we write this in the standard form for a plane, it becomes 2e squared x minus 1 plus 2e squared y minus 1 minus z is equal to minus e squared. And then so the normal vector for this plane, or a normal vector for this plane, is 2e squared 2e squared minus 1. This could be a normal vector for the plane. So this vector is normal to this plane, so it's perpendicular to the plane. That also means it's perpendicular to the surface at the point 1, 1 e squared. But notice that this is just the x derivative of f evaluated at 1, 1, and this is the y derivative of f evaluated at 1, 1. So now let's do that. So that's where this formula comes from. And again, if you didn't follow that, I just encourage you to think about it. Okay, so the first surface that we looked at, it was z. So we're just going to do each of the questions on this page. So actually, let me do a different color for each surface. So I'll start with blue. So part 1, we looked at z is equal to sine of xy. And we did this at the point 1 pi over 2, 1. Okay, and we saw that the gradient vector at this point was just the 0 vector, 0, 0. This is equal to the gradient of f. And remember, this is fx, fy. So the vector that we could take to answer this question could be v is equal to 0, 0 minus 1. And then remember, any scalar multiple of this vector would also be an answer to the question. Okay, now let's move on to the second surface that we looked at. The second surface that we looked at is z is equal to x squared plus y squared minus xy. And we looked at the point 1, 1, 1. And here we saw that the gradient vector is equal to 1, 1. So an answer to this question could be v is equal to 1, 1 minus 1. And again, any multiple of this vector would also work. Okay, and then the final surface that we looked at, that was the one that we just saw. Z is equal to the power of x squared plus y squared. And we did this at the point 1, 1, e squared. And we saw that the gradient of f is equal to 2e squared, 2e squared. And then so the normal vector, or a vector perpendicular to the surface at this point is v is equal to 2e squared, 2e squared minus 1. Okay, and again, any scalar multiple of this vector would also work.